Theoretically, designing an engine capable of reaching Mach 1000 is beyond our current technology and engineering understanding. However, we can discuss the basic principles and possibilities required for such speeds. Here are the characteristics an engine would need to operate at Mach 1000. 1. Propulsion system. Nuclear propulsion systems. For these speeds, beyond the limits of current chemical rockets, nuclear fusion or nuclear fission propulsion systems are necessary. These engines can generate enormous amounts of energy and provide long-duration, high-speed thrust. Ion engines. Ion engines can achieve high speeds by operating with low thrust over long periods. However, achieving Mach 1000 would require much more advanced and powerful versions of these engines. Antimatter engines. Antimatter engines, powered by matter-antimatter annihilation, could theoretically provide the energy density needed for such high speeds. 2. Fuel and energy management. High-energy density fuels. Achieving these speeds requires fuels with extremely high energy density, such as nuclear or antimatter fuels. Efficient energy conversion. The engine must convert energy to thrust very efficiently, minimizing heat loss and other inefficiencies. 3. Heat management and material science. High-temperature materials. Materials capable of withstanding the extreme heat generated at Mach 1000 are essential. These materials must maintain structural integrity at high temperatures. Heat management systems. Advanced cooling and heat management systems are necessary to distribute and manage the heat effectively. 4. Aerodynamic design. Low drag. Efficient aerodynamic design to minimize drag at high speeds is crucial. This reduces the negative impact of air and other gases on propulsion efficiency. Plasma shields. Technologies such as plasma shields might be necessary to manage the plasma created by high-speed collisions with air molecules. 5. Orbital dynamics and navigation. Advanced navigation systems. Highly precise and reliable navigation systems are required to maintain trajectory and correct minor deviations. Orbital transfers. Efficient space travel between Earth and Mars may involve orbital transfers and gravity assists. Theoretical and practical challenges. Achieving these speeds with current technology is impossible. However, future advancements in nuclear propulsion systems or antimatter engines could make such speeds theoretically possible. Developing these engines would revolutionize space exploration and long-distance space travel. Materials for Mach 1000. Developing materials capable of withstanding Mach 1000 speeds is beyond our current technology and material science. Here are some theoretical possibilities. 1. High melting point materials. Tungsten. With a melting point of 3,422 degrees Celsius, tungsten is a candidate, though its density limits its use in spacecraft. Tantalum carbide and hafnium carbide. These ceramics have melting points around 4,000 degrees Celsius and are highly heat resistant. 2. Composite materials. Carbon-carbon composites. These materials, reinforced with carbon fibers, offer high temperature resistance and low density. Ceramic matrix composites, CMCs. Used in space shuttle heat shields, CMCs provide high temperature resistance and oxidation resistance. 3. Graphene and nanotechnology. Graphene. This one-atom-thick carbon material offers excellent thermal conductivity and mechanical strength, though more research is needed for large-scale applications. Carbon nanotubes. Providing high strength and thermal resistance, carbon nanotubes can be used in spacecraft structures. 4. Heat management and protection systems. Thermal protection systems. High-temperature resistant systems protect spacecraft from extreme heat. Active cooling systems. Liquid cooling and phase change materials manage heat for high-speed spacecraft. 5. Surface coatings and protective films. Ultra-high temperature ceramic coatings, UHDCs. These coatings increase temperature resistance when applied to metal or composite surfaces. Ablative coatings. These materials vaporize or peel off, removing heat and protecting the spacecraft. Theoretical and experimental materials. Metallic hydrogen. This theoretically extremely strong and thermally conductive material has not yet been produced in a stable form. High-temperature superconductors. These materials could offer energy efficiency at high temperatures, though more research is needed for space applications. Developing materials for Mach 1000 speeds pushes the boundaries of current technology and material science. Advances in nanotechnology, advanced ceramics, and composites could make these materials possible, crucial for future high-speed space travel.